It, okay. They're information processing paradigms inspired by the way biological neural systems process data. So to go into that more in depth, similar to how the human body's biological neural networks, our brain works, neural networks have a layered architecture of neurons that connect with each other. So in neural networks, each network node on a connection point, we call them a neuron, has the capability to process input and forward input to the next node, kind of similar to how neurons in our brain works. So here on this slide, we're drawing a very direct comparison between a biological neuron and a neural network neuron. To shorten that term, we call a neural network neuron an artificial neuron. And in its essence, an artificial neuron is just a mathematical function. It helps facilitate the transfer of information from one layer to another by processing the information in that function. An artificial neuron is the basic unit that makes up a neural network, and there's many different variations. So for example, a artificial neuron can be a logistic regression function, also known as a sigmoid function, a linear function, so like y equals mx plus b, tanh, or like a ReLU unit. So there's a lot of different mathematical functions that can be used in an artificial neuron. So here on this slide, we're going to go through an example of how a neural network would process information. So in this example, we're going to pretend that we're trying to predict if a lung cancer patient will go into remission. So the output is either they go into remission or they don't. In order to figure that out, we have some features. So for each patient, we know these features or kind of just characteristics of these patients. In this example, we'll say, we know their age, their number of PAC years, and the size of their tumor. This is not medically correct or anything, it's just for the sake of this example. So say in this case, we have these three features. So these will go into the first three circles, and this forms what we call the input layer. This is pretty straightforward, just as many characteristics as you have, that's how many circles you have, and that forms your input layer. And this is all for one patient. So in the next layer, as it feeds forward, these input features feed to the next layer. This layer is the artificial neuron layer, like Ricky said, he's put here examples of the functions. And here, just for processing sake, we'll say there's 4 neurons. And like we previously said, neurons are mathematical equations. These equations are called activation functions. That's just a term they're called. We don't have to think too much about it. And in this case, for simplicity, we'll say that the activation function is logistic regression. So each feature, in this case, age, PAC years, and size, will feed into each neuron in this layer. We call this layer a hidden layer. And the purpose of this layer is to learn how to combine these features optimally. It will try every combination of features from our data in order to learn the best way to combine features. And that's why each feature will feed into each neuron, and each neuron will combine them differently and run them through the mathematical equation. And then moving right one more time, you have the output layer. So this is a final layer of logistic regression functions that will tell us whether or not this patient will go into remission. So again, each neuron, the hidden layer, will pipe into the final output layer, and that serves as our final hypothesis and calculates the result. In this case, the result is if the patient will go into remission or they will not go into remission. So as you go through these steps, you can kind of see how the network runs. But the next part I'm going to quickly go over is how the learning part happens, because this part is just how it runs for each patient, but the learning happens after the output layer. So after the output layer, it'll say remission, no remission, and then you have a loss function. This loss function is just another mathematical equation that calculates how off the mark you were or if you were correct. This loss function is applied backwards to all of the hidden layer neurons and optimizes them. So if we were kind of to think of this in a more quantitative mathematical way, we can say neuron 1 had the equation of x plus y plus z. So age plus PAC years plus size. That was the relationship we decided between these 3 variables, just adding it. So then say after we optimize it, backwards, we call this back propagation. We improve on the equation and say now after optimizing it, we change the weights of each feature to 2x plus 3y plus 4z. So basically each time you go through a new patient, you calculate the loss, see how off the mark you were, and then you go backwards and improve on your hidden layer neurons and then try again. So each time you go through a new patient, you're learning how to get closer to the mark. That's a huge simplification, but essentially to help myself understand what goes on in a neural network, that's what works best for me. So that in the end, after this process repeats itself for every single patient, the network learns, and at the end, hopefully it's pretty good at predicting the answer. And that's kind of why we always say neural networks need a lot of data, because they need to repeat this process again and again and again in order to get better at it. So then going on to the next slide, Ricky, can you go to the next slide? So just now, we went over an example with one hidden layer. And that's also a simplification because there can be as many layers as you want. There are different types of neural networks that have hundreds of layers. They have even thousands of layers and up to 1 million parameters in the input layer. So neural networks, how I like to think of neural networks is that they're almost like a magical broad spectrum antibiotic that can adapt to any situation, any infection. And this includes a lot of complex relationships and problems. So relationships like I mentioned, if a patient is going to remission or not, it's not really a simple, multiply these variables or add them together. We're not really sure how these relationships, how these features actually correlate with each other. And when that happens, that's a good networks. But neural networks are also, like I said, they're like a magical broad spectrum antibiotic. So you can use them for these super complex problems, but they also do work for very simple problems. And unfortunately, that also means that there are cons with a neural network. So one of the cons is that when you run a neural network, you really have no idea what's going on. You basically run the neural network, it goes through all these hidden layers. I've run ones with hundreds of layers. I have no idea what's doing in between each layer. And when things go wrong, it's really difficult to figure out where did things go wrong. You can't really walk yourself through each step because it's not possible to compute all these hundreds and thousands of features to figure out where it's going wrong. Ricky, next slide. So while neural networks, before I go to the next part, Ricky, do you want to talk about another quick neural network example?
Yeah, so this is an example of a higher dimensional neural network. So in the previous neural network, your input was a singular value, like the age or number of pack years or the size of the tumor. What's popular are convolutional neural networks, where your input is not a singular value anymore, but rather a matrix of values. This is most popularly used for videos or images, because an image is just a matrix of numbers. A CT image is a matrix of grayscale numbers. So how do you use that in a neural network? You need to take portions of that image, which is a smaller matrix, and then your mathematical operations, instead of input as single input to the function, it's a matrix multiplication or a convolution. And then those matrix that's multiplied by are the ones that are adjusted now instead of just the weight. So this is known as a convolutional neural network. It's what's popularly used for medical images, but it's the exact same principle. There are weights in between and mathematical functions in between that are repeatedly optimized when more data comes in. So the question is that, okay, what do these activation functions in a convolutional neural network look like? Well, like I said, they're matrices of numbers specifically to extract certain parts of the image. So if you look at, for instance, the top left neuron, this is something where you see it's zeros around the center, and then there's an edge of there's ones near the center, and there's edge of zeros, which is where the black is. This will extract the bottom left segment of the image and highlight what's in the center. So if there's an image that is significant, where there's something really significant in the bottom left, for instance, if you're looking at X-ray and you're looking for right lower lobe pneumonia, this top left kernel will give you that region extracted. So that's an example of a neuron and convolutional neural network. So you can see it's quite hard to interpret. sort of interpretable, but as you get deeper in layers and when these multiply with each other, it's really difficult to interpret.
So yeah, so a convolutional neural network is an even better example of why it's really difficult to understand what's going on in a neural network and why it's hard to fix it when it's going wrong. So while neural networks and convolutional neural networks can be used for almost every problem, you probably shouldn't do that, just like how you probably shouldn't use broad spectrum antibiotics for every single situation either. So why specifically shouldn't you use it? We talked about how it's really hard to figure out what's going on, but in addition to that, neural networks are expensive. You can't always run a neural network on, say, like your MacBook. You need a GPU and like an expensive one too. So you may have to rent a GPU or rent time on Amazon cloud services or on Google Cloud services to be able to even run this network. It's time consuming. I run a neural network once that took I think it was like a week and a half to run. And afterwards, after a week and a half, the result, I realized I made a mistake. So I had to just rerun it completely from scratch. And like we mentioned, a big part is that you can't explain how you got the answer that you got. And I think you can kind of see how that can be problematic in a lot of situations where you're presenting a solution to someone and you have no idea how you got there. You can't show your work. And the way that we referred to this is called the black box effect. You probably see this talked about a lot, this supposed black box effect. It's really like a major con of neural networks, especially in this medical setting. So it is one that is very important to talk about. So to avoid all of these cons, you can use one of the other many machine learning models. A lot of them are ones that Ricky went over previously. So sometimes instead of using a neural network that will take a week to run, you can use a logistic regression function, maybe even a linear function like y equals mx plus b, or a random forest, that's really great for clinical algorithms as well. So there's all these different options that you can use rather than just applying neural networks to every problem that you encounter. So yeah, if anyone has any questions right now, feel free to ask me or Ricky.
Yeah, feel free to ask in the chat. And also in the end, we'll stop the recording in case anyone wants to ask any questions then.
How do you choose how many hidden layers you need? Or is that something the computer does?
I can pipe in on that. So we don't know. That's a very lazy answer. In terms of choosing, there's a balance because when you have too many layers, you start overfitting. When you have not enough layers, you'll start to lose resolution. So usually, for instance, for images, you want like 50 to 100 layers in literature. That's what's been tested. For point data, you do the same sort of hyperparameter optimization where you sweep through a lot of different combinations of layers and you see what gives you the best balance between testing accuracy and efficiency, for instance. So it sucks. There's really no, it's like, as far as I know, there's no known answer. It's a lot of trial and error and tuning depending on how specific your scenario is. If you need a really generalizable network, like it needs to work on multiple machines, then you can't have it way too deep, for instance.
Yeah, I think it also depends on kind of like what kind of neural network you want to use. There's all these like famous ones. There's almost like kind of like trends, like clothing trends, like back in, I think like 2014, 2013, they came out with like Resident and such, where they just added like a ton and tons of layers. And that was kind of like, the new thing at the time, adding like a ton of layers and then being able to backpropagate quickly. That was a trend at the time to add more layers, and then later there's a fission net that kind of like cuts down more on the layers. So there's really not like a perfect answer. Usually, you try different combinations. Depending on the problem you have, you may want to try like the newest trend in neural networks. But like Ricky said, there's no straightforward answer.
Thank you.
Now, talking more specifically about neural networks and why they shouldn't be used for every problem. Something else that we need to be aware of is the fact that neural networks are very sensitive. Small changes in your image or say in your data can completely change how a neural network analyzes the image or the problem. So on the next slide, we have an example where, to us, to the human eye, these two pictures look really similar, but a neural network would classify the one on the left as a pig and then one on the right as an airliner. And the reason for that is when you actually look at the specific pixels of these images, which is what the neural network looks at, it'll look at like specific like kernels of these pixels, like a 3x3 pixel, then like go over like you're taking like a small magnifying glass and like looking at each specific area. And then when it does that and like kind of builds everything up, it comes up with a completely different answer.
Yeah, so there are some techniques you can use to improve convolutional neural networks and neural networks. One big thing is data augmentation because of how important a lot of data is to make sure you're not overfitting. A lot of researchers do a technique where they slightly modify data, but they still maintain the key idea. For instance, in these images, you have a picture of a bird, but you're adding blurs, you're sort of adding pixelations, adjusting the brightness and contrast. So the images is changing slightly, but the key concept, at least for human interpretability, is still there. From a human eye, this is all still a bird, but this is really testing the neural network if it can handle different situations where there are slight variations in the data. This is an example of, it's a famous example of the Eiffel Tower, where you're just slightly changing the angle of the image. Some of the images are flipped and some of them are translated. And this is generally a really, really good idea. If there's any paper out there that's implementing a convolutional neural network and they do data augmentation, that means they further validated their method. And this is something that I look for to validate existing technologies. So now I know that was a really quick rundown of what a neural network is and what a convolutional neural network is. I don't think we need to know more detail than that to, for instance, say like, hey, let's try a neural network for this problem. But if there are any questions, feel free to ask at this point. Last time we ran this, there were a lot of questions, so just making sure we're covering all the bases. And also always feel free to pipe in the chat too. Okay, so this is, again, this is a really useful diagram that even I refer to a lot. This is a plot of sensitive interpretability compared to accuracy. And you see neural networks, they usually perform the most accurately just because they're so complex, they're going to catch every single little detail, but they're not interpretable at all. Whereas a random forest, a support vector machine, graphical models, they are completely, to me, they're a completely 99% interpretable. Any medical student, doctor, physician can interpret what it's learning and also interpret like its limitations. So the question would then be like, which one should I pick? For publications, people usually want to hop on to the most accurate methods, which is why you see so many neural networks in publications. But for actual practice, it's not always used. In fact, for clinical guidelines, the machine learning methods used to develop clinical guidelines, I really see support vector machines and random forests more often than neural networks. For images, it's convolutional neural networks. That's the king right now. And there's this principle where if your models perform the same, and by same I mean within 0.02, like within 1 or 2% accuracy, usually the simpler model is the one you want to go with because that's likely not overfitted as much as a more complex model. Okay, so we're going to go over this example. This is a really famous paper. This is from Stanford, I think. They created this deep learning convolutional neural network method to try and predict chest X-ray pathologies. They name it ChexNext, which interesting name. They have a really high affinity for X's, I guess. Anyway, so it's the link to the papers at the end. So I'll just go over the main results. They have over 100,000 of posterior, anterior, posterior X-rays of over 30,000 patients. So this is an amazing sample size. This is, Nature or New England Journal of Medicine level sample size. And each image has 1 of 14 thoracic pathologies like empyema, consolidation, pneumothorax, I think. So this is the distribution of different pathologies. And you see they have a pretty good split, right? Mostly it's atelectasis, effusion, infiltration, consolidation, your usual bread and butter chest X-ray pathologies. So their method was that they used a convolutional neural network, which again is multiplying that matrix with a series of matrices in between using 121 layers. So it's 121 layers of matrix multiplications that are always adjusted. So completely uninterpretable. I have no idea what it's doing. Even when I open it up, I have no clue exactly what part of the image it's looking at. So when they validated the method, they had a set of 420 frontal view chest radiographs with 50 cases of each pathology, which is, it's not like, oh, I would prefer the validation set to be larger, but it's not that bad. When it's annotated by different radiologists, which is great. You always want different expert annotations. This I have no problem with. So this is a visualization of the results from the convolutional neural network. I know I said it's uninterpretable. There are methods to try and extract the regions of the image that the neural network is looking at. This is one such method. So you can see it is looking at parts of the image that are significant. For instance, here you see on the right side, you see the opacity in the right middle lobe, and the neural network highlights that opacity. So it's able to localize where it should look at most of the time. The disclaimer is that these are cherry-picked images for the publication, so your mileage may vary when you actually implement it in practice. These are the area under the curves that they reported, and they all have quite good AUC, right? They have good sensitivities and specificities. Certainly for different pathologies, there are different accuracies. Things like hernia, much lower accuracy than, for instance, atelectasis or edema. And that kind of makes sense because when you think about overfitting, you always think about what data is not available. There weren't that many cases of hernia, so the network isn't able to learn hernia as much. But that brings a question, like, do I trust this neural network if I put it in practice? How do I know how much data is enough? This network looks like it's able to predict effusion and edema quite well, but not hernia. So it's not like a human where you train them in, let's say, 50, 100 cases, and they're able to sort of generalize afterwards. That's a drawback of using these neural networks. They also reported a whole swath of results, which is great. They reported the kappa statistic, which is inter-rater agreeability, the sensitivity, specificity, and they also compared the accuracies between the neural network and the radiologists. So after going through this neural network, after going through some important parts of this paper, is this a win for artificial intelligence? Well, yes and no. So overall, when they externally validated to radiologists did better on average. It was mostly the same as the radiologists, but they still performed better, especially for cases like hernia or even pneumothorax, where how the image looks is vastly different from like an empyema or a consolidation. However, it's very, very fast, right? 420 scans in 90 seconds compared to radiologists. Those poor radiologists that they used for this study, they had to take 4 hours each to go through all those scans. And it does not require an expert. So this increases efficiency, right? So you can start to see the story that's being molded here. It's not something that's good enough to replace a physician, but it's something that's fast and quick and can hit the high yield bread and butter pathologies, which means that you can implement this, for instance, as a screening tool in a low resource area. And then you can use that to screen to see if this patient has concerning pathologies that need to be referred to a physician. Now, there's also an economics question that comes out of this, because chest x-rays are quite cheap, right? And so if you have symptoms that warrant a chest x-ray that would require radiologists in our current pipeline, would you use this is this a useful screening tool? Because there are several principles of screening where usage of the screening means that we can catch something efficiently and cost effectively, and we can implement an intervention that we couldn't without screening. But in our current pipeline, especially in Canada, chest x-rays are cheap for pneumonia. So it's not something you'll likely see implemented in a country like Canada. So I'm going to go through some big points to take away from the last few weeks.
Sorry, Ricky, can I just interrupt for a second? I was just going to say something else to take into mind with this example of chest x-rays. For an example, like here at Queen's, overnight, plain films aren't read at all at the Kingston hospitals. So overnight, if you order a plain film chest X-ray, abdo X-ray, any type of X-ray, like a radiology resident or radiologist will not read it until the next day. So overnight, only CAT scans and MRIs are read. So, that's also something to consider in these cases. Maybe it could be helpful for, say, like a merge physician or internal medicine physician to have like a tool like that, kind of points out maybe you should look at this closer. It's also like something to think about. And like Ricky mentioned, economics, radiologists are paid like $5, $4 for one chest X-ray or like any plain film. And oftentimes it takes a lot more time than you would think to go over a plain film. So there's definitely areas where this may be, implemented and may be helpful, but it's more of like a tool that could be helpful. Yeah, sorry, Ricky, go.
No, that's great points. Yeah, so we have some big takeaways from this. Is from machine learning, artificial intelligence in general. So from all the examples we presented, artificial intelligence really is just advanced statistics. You're trying to predict something, but now we have this advanced statistical tool that can constantly update and make better predictions. It's not this abstract robot that does everything by itself, that has mathematical magic in it. It's something that is completely human driven and human designed and human constrained, which means that each one of us can contribute to improving machine learning, right? Clinicians have a role to evaluate machine learning in the future in clinical practice, because physicians are going to be entrusted in evaluating new tools coming into the hospital. So it's things like, for instance, checking that whatever patent or whatever technology coming in, they've been properly tested, they've been properly cross-validated, they have proper data balancing, and they're not overfitted. That's something that any one of us can do. And knowing the capabilities of limitations of such methods, such as when it's able to be accurate, in what cases it's applicable and what's not. For instance, that ChexNet, I would not trust it for a hernia or even pneumothorax, right? And there's a trade-off between how complex a model is and how interpretable it is. Remember, two weeks ago, we went through the pediatric CT scan score, where they've made their machine learning resulted in a flow chart where you first assess the GCS and you assess the mechanism of injury. And that gives you a treatment decision. That's completely interpretable, right? They give you a score associated with this symptom, where something like ChexNet, that's not really interpretable. But as uninterpretable it is, don't be intimidated by it. We can still evaluate it and assess if it's usable in clinical practice. And the question always comes up like, okay, with this information, what can I do as a med student, right? Like first thing, as mentioned before, you can help audit new machine learning tools or technologies coming into clinic in the future, right? It's like how radiologists have to evaluate a new MRI sequence or a CT protocol when it's created to see if it's valid for your patient population. You can also play a more development role where now you have the tools to identify clinical problems that can be targeted by machine learning, such as if you want to predict some sort of outcome and you have a lot of numerical clinical data. Well, now instead of using classical logistic regression, now you can use methods like a support vector machine or a random forest. These are methods that are very commonplace in literature, and there's code existing online where you can take the library, and even an undergraduate computer science student or a med student with about a year or two of training can start to implement some rudimentary analysis with it. And also hopefully know now that we all can speak some of the language, that you can collaborate with engineers and data scientists in the biomedical engineering realm to design these problems and to design solutions for these problems. So there's a lot of things that med students and clinicians can do. So this is an example of something that's already in clinical practice. This is Rapid AI, which is software for stroke perfusion, visualizations. So they take in CT scan images and they use machine learning. I don't think they published their methods. This might be somewhere deep in the patent, but I didn't read their patent. But they use a combination. It looks like a combination of neural networks and some sort of point data classifier to try and visualize which part of the brains are ischemic. So you can see there's some utility to this, right? A stroke patient comes in, immediately they go into CT scanner and we can visualize which parts of the brains are salvageable, which are not. And also for different protocols that require some percentage of the brain to be infarcted. So this is currently used at Queens at KGH, where the neurologists and sometimes the radiologists look at these images to sort of guide treatment decisions. And when I say sort of, that segues to my next point. The question is like, how useful is a software like this? Because it's nice, it gives us a visualization of perfusion. It might gives us some prognosis or prognostic assessment, but it also doesn't replace radiologists and doesn't replace neurologists. You're still going to need the radiologist to locate the infarct, and you're still going to need the neurologist to perform the physical exam and decide if the patient is going for, TPA or going for a thrombectomy, for instance. So it's not a physician replacement tool. And it's just another physician assist tool. It's like I said, it's like another sequence in CT or another sequence in MRI. It's new information for physicians to use to guide their treatment decisions. And this is really in the next 10, 15 years where machine learning is going in medicine. So there's a big role for physicians. These are some links that we'll post online on the website of the paper, and they have a nice project page where they advertise the project and everything. And there's a workshop survey at the end, but I'll go over the programming example first. So this is quite a dense program example. I'll send a link to everyone, and then everyone can run it on their own time if they want. So let me just share the link on Zoom first. At any point, if you have questions, feel free to ask in the chat. I know this session is quite dense. All right. There you go. Okay, if anyone wants to run the code along with me, the link is in the chat. Again, to run the code, first thing you need to do is go File and Save to Drive, so you have your own copy. Since I have the original copy, I don't have to do that. Again, everything's segmented into cells. To run a cell, either press the play button or hold shift and press enter. Right, these are text cells. You run it, it says like this text is text. So first we're gonna load some libraries. This is the usual library importing. It's nothing special here. And we're gonna use the exact same data set. So we use the breast cancer data set that we've been using in the last 2 weeks, where there's, I think, 29 different features, and you're trying to predict if the patient has malignancy or a benign tumor. This is just loading the data and splitting into training and validation sets. So, and we'll try a neural network. So arbitrarily, this is a neural network we're going to create. It has 4 different layers. It has, and this is sort of the architecture. It's just expansive in one direction. It's not the best one, but it still performs with high accuracy. You'll see. So this is the definition of the layers. We're gonna create some hyperparameters, which is, for instance, the maximum number of iterations that we want to run before we say that, okay, the accuracy is, stop trying to improve the accuracy, we'll be overfitting afterwards, right? Next 2 lines creates this neural network object. It's called MLP. That's because the original name was multi-layer perceptron. I don't know why, but I don't know why they changed the name as a cultural shift, I guess. And we're gonna plot the accuracy. So we're gonna print the accuracy after training and validation. So this is just a really simple, I'm just telling this existing library, create this neural network for me and training on this data and give me the accuracies. So I'm gonna run this cell. And so the accuracy in the training set's about 98%, and the validation set's about 97%. So from the random forest method, we tried decision tree method, not random forest. I think the accuracy testing set was about 96%. So it does perform marginally better. And if you look at the confusion matrix, it performs excellent. So if you took this code in a time machine and went back about 25 years ago, you'd probably win best paper at a conference. But so there's a question in the chat. How is the architecture for this neural network decided? So completely arbitrary. In general, you want at least like 3 to 4 layers to start with. And within each layer, you can have a depth of, let's say, 5 to 10. So here, this is, in this line is where define the number of layers and depth, which is on the low end. In practice, if you want to optimize, you'll create a loop and you loop through different values of layers just to see like what combination of layers and depth works the best. But there's no real answer as what the best combination is. That's still unknown to literature. If you find out, you'll win best paper at the top machine learning conference. So this is an example of a point data neural network. Some people call this an artificial neural network. Some people call it a multi-layer perceptron network. It's all the same. It's a very simple neural network. So we're going to try, next we're going to try a convolutional neural network. So this is where it gets a little bit complicated in terms of semantics, which is like the specific code to call the proper function. It's nothing like, it's nothing that's cerebral. It's just a lot of specific keywords. So we're going to create this neural net. So a convolutional neural network has different hyperparameters than a regular neural network. For instance, what people commonly use is the batch size, which is how many images the neural network would take at once. Because these are so computationally expensive, you can't use all the data at once, like the point data network. We can also adjust the learning rate, which is how much the weights are optimized each time. If the learning rate is smaller, then yeah, we'll get a finer resolution on optimization, but it'll also take forever. And we also might be stuck at some area where the network thinks it's optimized, but it's not. So the question that's still in literature is, what's the best learning rate? It's unknown. Most commonly, I want to say 90% of papers go use either 0.001 or 0.0001 just by convention. So you can start to see how like unintuitive some of this stuff is. And a lot of this is throwing stuff at the wall and seeing what sticks. We're going to have to import a specific library called PyTorch. And we're going to tell Google, we're going to use Google's graphics cards. So if you run this on your own computer, I think if you don't have CUDA libraries, it's a bit hard because NVIDIA is really the king of convolutional neural networks right now, unfortunately. Okay, and then we'll go download this data set. So, oh no. Okay, I think because I already downloaded it, it's giving me an error. I think because it's already there. But if you run this, it should tell you like, oh, we downloaded this data set. Yeah. Okay. This next part, I'm just summarizing what's in the data set. So there's nothing theoretical about neural networks in this next code section. So inside this data set, there are about 60,000 images in 6 different categories. They're images of chest X-rays, hand X-rays, chest CTs, abdo CTs, head CTs, and breast MRIs. Right? And the dimensions of each image is 64 by 64. The next cell visualizes what some of these images are. It's just plotting it in a 3 by 3 grid. So I'm going to run this, and you can see these are what the images look like in this data set, and there's about 60,000 of these. Okay. Now this next section helps me transform the image and make sure that each image is labeled with its correct class. We still haven't run the convolutional neural network. A lot of this is data preparation. Okay. And then this next part tells me to load the data into memory because there's so many images and it's such a large size. A lot of computers don't have enough RAM to run it. A lot of computers don't import everything by default, so you have to specify how to handle the memory. Okay. So now let's see what these images look like after all these transformations. So now these images in the data loader looks like this. So it's going to feed into the convolutional network like this. Okay, now we can finally go to the convolutional network after all that data preparation. So here we're going to create a neural network that's we arbitrarily picked several different layers. So there's a convolutional layer, there's a max pooling layer. So a max pooling layer is when you take the original image and you sort of downsize it by taking the maximum of adjacent cells. If you're losing resolution, it's sort of like shrinking the image. And you do this because you really need to save memory when you go into the deeper layers. So, and we notice that even with this shrinking, we can still extract some useful features. There's another convolutional layer, and then the next 3 are fully connected layers. So instead of matrix multiplications, these are just going to transfer the image one layer to the next with some slight adjustments in weights, but it's not going to be a full convolution. I'm going to run this and then and just print out what the convolutional neural network looks like. So it's a very simple 6-layer convolutional neural network. Okay, now we have to define what our loss function is and what we need to optimize. So here, the most common loss function is called cross entropy, and the most common optimization function is called atom. I think this is actually, for a number of years, the most cited paper ever. So, and then we're going to finally run through the training. So each run through the data is called an epoch in convolutional neural network language. Don't ask me why. I don't know why there's so many esoteric names, but that's how it is. And then we're going to tell the neural network to, take this data and then optimize it, do some calculus, do a minimization problem by taking the gradient. And then that tells us which direction to optimize the weights. And then we're going to tell the neural network, okay, let's train through these epochs. So if I run this, I should start seeing the convolutional neural network training. Okay. Now, so what it's doing, it's going through those 60,000 images, running through the neural network, coming up with a prediction, seeing how off that prediction is, updating the weights, and going to the next image. That is essentially, it's the same machine learning pipeline, except now we're working with images. So each epoch, it tells me, how much the loss there is. The lower loss, the better. Okay, so this takes a while. I think this takes 2 to 3 minutes. So at this time, are there any questions?
So I have a question again. I think in one of the earlier, maybe in the first session, you were kind of mentioning that like to be able to use like machine learning methods, you have to have an inkling that there might be a pattern in the data already. So like, how would you kind of be able to figure out that there's a pattern in the data like before you actually use the machine learning? Like, what would you be using? Like gut instinct, or is it anything more than that?
Yeah. So there are two sort of schools of thought. One is that let's just implement any neural network and see if there's any accuracy above 0.6. Usually 0.6 is the cutoff. That means there's a signal and there's a pattern in there. The humans might not be able to sense that pattern, but there's a pattern in there, right? The other school of thought is that we need to do some preliminary statistical analysis. So usually if you're doing a classification problem, let's do a logistic regression on all the variables, which will give us odds ratios for each variable. And if some variable has an odds ratios with a significant p-value, we know the variable is related to the outcome. So we know there's a signal to work with, right? So those are sort of the two common techniques to do that. There are downsides of each. For instance, the first one, you're kind of not into, it's just trial and error, and you might just be overfitting. The second technique where you do a preliminary statistical analysis, you're limited because those statistical methods aren't very good at sniffing out really complex relationships. So if you get no good odds ratios and no good p-values, you might prematurely say, there's no signal in here, I'm not even gonna try machine learning. But there might be a really deep hidden signal in the data that you aren't able to sense out. So those are two methods that are commonly used. Does that answer the question?
Yeah, it does. I think it actually kind of added another question, but I think they kind of answered it as well, kind of, because like you were saying that like machine learning is kind of just like, it's kind of like an extension of stats. I was just kind of wondering like, why not just use like regular stats? But I guess you're saying it's because the relationships are so complex. Is that the main reason? Or
yeah, the relationships are very complex. And also for regular stats are very, very good to say that there is some statistical relation here. There is a good p-value. Patients with this, like patients that are older have a poor survivability compared to patients that are younger. When you're looking at single variables and saying these variables are very important, stats are very, very good at that. The classical stats are limited when you do predictive analysis, because what people usually do, they take those p-values and they create like scoring systems and everything. And those things are very limited because you're working with, you're doing a one pass through your data instead of iterating and improving your model. So for predictive analysis, which usually has a lot of complex relationships, it's quite limited. So that would be my answer to that question.
Okay, thank you.
Yeah, no worries. Thanks for the questions. Great questions, by the way. So we finished training. Now let's see our accuracy. So I'm going to run the cell, and the accuracy is, so every time I run this, there'll be slightly different accuracy because there's different random state that initializes the images on. But so the accuracy on 10,000 test images is 99%, which is amazing, right? Take a time machine, go 20, 25 years ago, you'll win best paper, you'll get a PhD from the best institution with this. And this is, you're classifying 6 different classes, right? We can also visualize the accuracy of the different classes, which I'm doing here. So this is, again, this is semantic programming. It's knowing how to use Python programming language to visualize different things. There's nothing intuitive to machine learning in this cell. But you can, of course, take this code, and if it's useful for you, you can take it, use it elsewhere. So it's able to predict the accuracy of each class quite well. And what you're doing here is a smoke test to make sure you're not overfitting for one specific class. Right? So next, we can plot this. This cell's useless. We can plot the confusion matrix to see where the errors occur. So we see that, okay, they're true positives. You're hitting the correct class most of the time. Maybe for when you're predicting, sometimes you predict hand when it's a chest X-ray, and you're off then, which kind of makes sense because these are the only two X-ray classes. Everything else is like CT or MRI. So there is some intuition in where the errors occur, and this error analysis is really helpful, especially when you're evaluating new machine learning technologies. Right. So what do we do here? We create a convolutional neural network that can classify a set of images into one of 6 classes. We're really classifying what anatomy and imaging modality there is. And the convolutional neural network is able to achieve it with 99% accuracy. Now, these are very, very obvious problems. For instance, when you're a human, you're looking at this, you can see it's obviously a hand X-ray, right? But when you're doing more difficult problems, like when you're trying to classify a breast MRI as malignant or benign, then it gets a little bit difficult and you won't see as high of accuracy here. So the higher accuracy here is just to a proof of principle. So now, before we end, there is a survey that I'd like to ask everyone to fill out. So I'm going to link this in the chat. I'll stop the recording for now.